it turned up, it looks like, I think what happened is in minor UNSW, it looks like we have tutorials in week 1, so I'm not sure why that happened, but if that caused you confusion, apologies, although actually there's nothing I could have done about it. So today, all right, I think the recording started, so welcome along everyone who's watching on the recording, welcome along everyone who's here in person. So today the plan is to continue on deriving the equations for linear regression. And I'll pick up from where we left off on Wednesday. So we're finding the parameters. Let me just switch to the tablet. And what we had was, I need to get a mic stand. These mics are just in the wrong place. And this radio mic doesn't seem to work. So yeah, I'll see if I can fix that for next week. So this is what we're trying to do. Just a quick recap. We have linear function. It's a simple linear regression, so we only have one variable x, one input variable x. We're going to generalize that in the second part of this lecture. We're doing optimization. We define our loss function. Remember our steps in machine learning. We define the model class, so linear function. Define the loss function, mean squared error. We want to find the best linear function in terms of minimizing this loss function, minimizing MSE. And for this, in this week, first week, we're taking the very standard approach of taking derivatives of this thing and set them to 0 and then seeing if we can derive an expression for that. So this is where we, this is where we finished on Wednesday. So we got to this point, and this was the end of the lecture and the end of the recording. Are we done? Are we done at this point? We've got an expression for A to minimize MSE, but are we done? What do you think? No, because we need an expression for B. There are two parameters. Sorry, I'm not sure where that blank slide came from. There are two parameters. So we have to find A, we have to find B. Loss function is a function of those two parameters. So let's just think about that for a second. It's a function. If we change, what that means is if we change the values of those two parameters, we can expect the loss to vary. And what we want is to find the minimum of that function, if possible. So we're taking the partial derivatives of both of these parameters. So we need to take the partial derivative to find the equivalent, find a similar expression for B. So we still need to find an expression for B. And just remember the notation here. This y bar is standing for the mean, the arithmetic mean, which is just the sum of all the individual y's divided by n. All right, let me switch to this mic, see if I can get it working. Can you hear me okay? Yeah, okay. I have to lean in very close, which kind of is weird, but... All right, hopefully everyone on the recording can still hear this. I'm going to lean in. If you have any questions, just shout out, because I'm sort of head down here trying to talk into this mic and write at the same time. So you can feel sorry for me if you want. All right. So actually, I might just take a new slide to do this. So we need to find an expression for B. Well, how do we do that? Well, we have the loss function. Taking the there are two components to this function, so we have to take partial derivatives. So d of the loss function with respect to second parameter B. Okay, so loss function, we'll just write it out again. Actually no, I'll go straight into this is 1 to n sum. Now, the sum is just, you know, if you imagine this summation just expanded out, it's you know, the first loss, the loss for the first example plus the loss for the second example, and so on. It's actually the squared loss. So for all of those, it's yi. So we're going to push the derivative into the sum, and so it's going to look like this, minus a minus bxi. So this time we are doing partial derivative with respect to b, sorry, squared. We're doing derivative with respect to b, so let's rewrite this sum. I'll just say sum I. Okay, so it's squared, so we have a 2, then the expression, and then we need to take the derivative for the expression inside, yi minus a minus bxi. Okay, any suggestions as to what we need to do here, or what we need to get for this? Before we had, remember, minus 1, but that's because we were taking the derivative with respect to a, right? And so the only thing that depended on a was a itself, so we ended up with minus 1. But here we're taking the derivative with respect to b. So, well, let's look at it. So the only thing that depends on b, the only component of the expression that depends on b is this. So, but what's that going to then end up being? This stays the same, obviously. Well, just suppose we're taking the derivative with respect to b of minus bxi. Minus xi, yes, that's correct, yeah, minus xi. So I'll just write it like that. Okay, and so now what do we need to do? Set it to 0. Okay, so if we look at this, if we, well, actually, let's be a little bit more correct, and I'll write this like this. So say 1 and sum I 2 yi bxi. Okay, anything you can see here that we can do? Well, yeah, the 2. Okay, so the constant can go, so we can get rid of the 2, well, we can get to 1n sum I. Okay, so we can do something else. We can get this xi to be over here, yi minus a. This is just for convenience. We can do that. Now we're heading in the same direction as we did for the previous derivation. So what we did, excuse me, what we did there was we tried to get an expression in terms of the means, because we want to get rid of this oops, we want to get rid of the summation over all these over all these things if possible. So we'll do essentially the same thing that we did before. So it's gonna end up looking, I won't go through the whole thing. You can check your reasoning and you'll have a chance to do this in the tutorial work for next week. So we can do this. We can expand this out and we can separate the components. So we can get this, and then we have A 1 over n sum xi, sum I, and what else do we have? We have a similar kind of thing. B, okay, so we have x squared this time because we've got xi times xi. Xi squared, all equal to 0. Now, looking back at this, here. So we will apply the same sort of reasoning here. We have taken the summation and turned that into averages. Okay, so we're going to end up with using the same notation. So this thing here is the mean of sum of the products, the x's times the y's for each example in the data. So that is the mean of the products, I should say. So we'll denote that x bar y. Now the second thing is this thing here. The second thing is the mean, or A times the mean of the xi's. So we'll write that A x bar. And then we have B. Sorry, that should be 1 over n. And then we have B, and this time we've got the mean of the x squareds. Okay, so it's x squared bar. You just have to be quite careful here with where the bar goes. So that means we can rewrite. So what do we need to rewrite? Well, we need an expression in terms of B. Okay, so we rewrite this minus bx squared, so we end up with B. We've got the product mean, that one, minus a x bar over x squared bar. Okay, so this is good. We've now got an expression in terms of B. Can anyone see a potential issue that we've got? Let me take a new slide, and then we'll have a look at it. So from before, we had well, let's look back. So we had this thing here. We've got A in terms of y and x and b, and we've got b in terms of y and x, or x and y and a. Right, so there's still an issue. So let me write that. Write that out to be totally clear. The thing we just got was xy bar, a x bar, x squared bar, and the thing we had before was y bar b x bar. Can you see a problem with this? Yeah. So we've got B is defined in terms of A, and A is defined in terms of B. By the way, you sometimes see people refer to this as the normal equations. Either this or the final form. But we've got we've got B in terms of A and A in terms of B. So that's a problem. What we'd really like is to have our expression just in terms of the data. And the data is just X and Y. So we want B to be a function. Let's say we want B to be a function only of the data. So what we can do is plug the expression. So B has A in its definition, so we can plug this expression for A into B and see if we can do anything with that. So let's do that. So we have B. Just try and make sure I get this right. Bxy minus, well, this is y bar minus bx bar. And then that's all over x squared bar. Okay, so we still have a problem. Is there a mistake? Say again? Yeah. Oh, okay. Sorry, I see what you're saying. Yeah, yeah. Yeah, so we've got a B on each side, right? Is that clear? So let's expand it out and see what we can do. So we've got xy bar. Okay, multiplying through, we're going to get, or I'll write it like this. Sorry, not multiplying, just expanding. We got x bar y bar minus b I think I've made a mistake in my notes. Hang on a sec. Yeah, sorry. I made a mistake here. Just give me a sec. So I think this is what people were telling me. We've got x bar here, right? Okay, that's what the mistake was. Thank you. Okay, so let's just, I don't want to take too much time for you. Just expand this out. I think this is all right now. Yeah, it should be okay, bx squared. So just note here, this is, well, let me finish this and I'll make that note. So you're just going to be a bit careful with these bars. It's not a great notation. So here, what we're saying is this is the average x bar squared, because this and this occur. But here, this is the thing we got from the original derivation of b. This is the x squareds, or the average of the x squareds, because that came from expanding out when we did the b derivation. Okay, so now we've got an expression with b on both sides. So I'll just do one further step. Oops. I'll just do one further step in the expansion. So we can write this like, just with some algebra, 1 minus the x bar squared over x squared bar. And then we get, this thing here, xy bar minus x bar y bar squared bar. And then to get b by itself on the left-hand side, we now have xy bar no, got to be careful here. Yep, this is it, minus x bar squared. Just let me, yeah. Yeah, okay. All right. So we're not sure about that, just sort of have a, yeah.
Like the second line, the last item, I think should be plus. But the answers at bottom, that's still correct. Because like you should, if you just open the bracket, you have to change the.
Oh, yeah. Yeah. Yeah.
Double negative expansion of brackets.
Just, sorry, one at a time?
So it should be like minus x bar y bar and then plus b times the x bar square. In the second line, the second equation.
This one.
In the second line, where it's minus bracket y bar minus b x bar, and when you expand it up x bar, the minus y and the x bar is minus x bar y bar, but then the minus times the minus b should be a plus b.
Yeah. Yeah, you mean this, right? Oops. You mean this?
Yeah.
Yeah. No, Yeah, okay. I'll need to go. I'll check this later. This expression, the expression at the end is right. I just want to. I'll check it later. If there's an issue, I'll fix it.
When you pull it back over, it becomes negative.
Yeah, yeah. No, I just want to. I just want to be clear later. Looking at it now, I'm just not sure if that's the best way to present it. Okay, so there's one other. Okay, anyway, let me just. Well, okay, let me just keep going. I'll review this after the lecture, and if there's a better way of doing it, I'll put it in the slides. Okay, so what we, at least this looks right to me. I think, yeah. Yeah, this looks right to me. But as I said, I'll review it afterwards, and if there's a problem, I'll fix it. Okay. Yeah. No, I think this is okay. I think this is okay. Yeah, I think this is okay. All right, sorry about that. Right, now, where am I? Okay. So this gives us a solution. We can find A, we can find B from the data, and then we can find A because we've now got B here. Now, what does this thing actually mean? Well, I'm not going to go into it now, but there's a way of there's a way of interpreting this that I want to talk about, and it's in the lecture notes, the printed lecture notes. So let me now go back to that, and I'll talk through an example. This thing, what I want to do is try and understand this thing in the context of what the data is actually telling us. Okay, caps lock. So let's look in the context of this example that I had before. So we'll say that the function we want is weight. So we have a sample of people. and the function is weight in terms of height, and we'll say that it's a linear function. So h is the input, x, and w is the output, y. So in this case, w will be a plus bh, the regression equation. And we want to minimize sum of squares for this. Okay, so if you do this, the approach is the same one that we took. So we have DDA of this specific. This is MS. This is actually not. It's not written as MSE, but anyway, you'll get to the same equations that we had. So this is A, or A hat, because it's an estimate of A, in terms of weight average, B hat, height average. The second, so that's fine, that's essentially what we got before. The second is B, or B hat, because I didn't put it in the hats because we're just deriving it, but essentially it is an estimate. But if we look here, the expression is a bit different. Now, I'm not going to go through it. I'll put a link to a video in which our course admin has got a derivation of this, which relates to the expression we derived, B. So you can, if you're interested, you can follow that. But what I want to do is go through this in terms of an interpretation, because this, so the version, let me just go back to the, right, this version here, I mean, it doesn't look very, it's not particularly understandable in terms of what this might mean, right? Because we've got product of the x and y's, we've got product of the mean, we've got the mean of the product x, y, we've got the product of the means x, y, and we've got the mean of the x squareds, and then we've got the square of the mean of x. If you've already seen this, you might know what this, you might be familiar with an interpretation of this, but in the denominator. But the numerator is a little bit more obscure. But as I said, you can derive this expression here for B in terms of that thing that we have, that we got before. So let's just look at this. So if you believe me, and I'll, as I said, put up a link to a video in which Omar derives that for you, you still have to sort of look at this thing and say, well, what is this thing telling us? Well, it actually does have a sort of interpretation. If we look at it, we're saying sum I1 to n, so over all of the data, and we've got x and y, h and w. And it's saying here, sum for each of the i's, the product of the difference of the hi to its mean and the difference of the wi to its mean. And then in the denominator we have sum over all of the data of hi from its mean and square that difference. Does this remind anyone of something we talked about on Wednesday? Sorry, just speak up a bit. Covariance over variance, yeah, exactly. So this is, remember we said covariance was the difference on all of the data from its mean for each of the two variables. And then the variance is, in this case, just for the input variable x, the difference from its mean squared. So one way of thinking about this is, particularly for B, or what does B represent? Well, A is the intercept. Okay, so by the way, I'll explain what this plot is. So this is, let's say sample n was 10, and we're measuring weight in kilograms and height in centimeters or meters. So this is height, this is weight. So this is telling us that this is the linear relationship. Now there are actually two lines here. So the red is the true model. Sorry, the red is the fitted to the data. So these blue points are the data. The red is the fitted line, and the data were generated randomly from the true function with some added noise, Gaussian noise. And we'll talk a bit more about that next week. So what that is telling us is that the fit is quite good. It's not exact, which is fine because there is noise added. But the question we're asking is, well, what is this, the B parameter? What does that mean, right? It's the slope of this fitted line. That's what we're finding. So A denotes the intercept value, and B is the slope of the regression line. And because we only have simple linear regression, it's very easy to see that on the x-axis. Now furthermore, maybe a bit faint, but you can see it on the PDF of the slides. This is the intersection of these dotted lines, these orange dotted lines, is that point there. And that point there represents the xy coordinate mean height, mean weight. And so it's about 180 something centimeters and 75 something kilograms. And just on the noise, so the noise added was normally distributed or Gaussian, mean 0 and variance 5. Okay, so, and it says here that the original model, the slope was B equals 0.83. So what is B? Well, there's an interpretation that we can apply. So B is the change in y for a unit change in x. So whatever the units of x are, if we increase or decrease, positive or negative, we can expect to see that much change in y. So B will tell us. So 0.83 on the true model. So I mentioned causal interpretations on Wednesday. Strictly speaking, you can't make any causal interpretation from this, but under certain assumptions, and if you have a random assignment of these values, then you can get into causal interpretation, but I'm not really going to go there here. Now, this, in simple linear regression, this slope is a measure of the relationship. But unlike correlation, we can, leaving aside the causal interpretation, which is important in applications, but leaving that aside, we can interpret this a bit more than correlation. We know about the direction, we know about the slope, and therefore we know about the relationship. So if, for example, b was 0, just by reasoning from the equations we've derived, well, we know that there's actually no relationship between y and x. The only thing we can say is that because bx is going to be 0, then the only thing that we can say is that the estimate of y hat, equals to a. And that will be y bar, so the mean. So if there is no relationship between x and y, the best estimate of y is the sample mean. As was said before, b hat is interpreted as the covariance over the variance in x. So this notation here, you may have seen, sigma is usually standard deviation. So we can think of this as standard deviation. I don't recommend using this terminology, but you can think of this as standard deviation and x times standard deviation y over standard deviation squared. Standard deviation is the square root of the variance. And so that's what that notation means. So it's the covariance between x and y in proportion to the variance. So what is that telling us? Well, if you think, someone asked me this question on Wednesday about covariance and variance. So if you think about it, if I have a lot of variance in my data, like there's a lot of difference between values in the sample and the mean of that sample, then that tells me, you know, this, if I see covariance of a certain size, I have to be careful about the interpretation of that. So it's not just if covariance, you know, moves around between x and y in the same way. That tells you that there's a relationship, or there could be a relationship. The magnitude of that covariance needs to be taken into account relative to the amount of variance in the actual data. So that's one way to think about what's going on here. And furthermore, if you know the units, we can understand what's going on in terms of the x units times the y units. So if we had well, we said centimeters, but let's say meters. Meters times kilograms is the covariance, right? So x was the height, y was the weight, meters and kilograms respectively. Those are the units. So the covariance is in meters times kilograms. The variance is in meters times meters, meters squared. And then if we think about their ratio or their quotient, that's units of y per units of x, kilograms per meter. And that goes back to what we said, right? The change in y that accompanies a unit change in x. So that's the interpretation. So, you know, in many applications, so this is fine for linear regression because it's this is simple linear regression as well. It's a very simple model. But it is worth thinking about what it means to interpret a machine learning model. Because although that's not always possible, it can be important in applications. It's not possible if you have, well, if you're not using linear regression, it doesn't have this form anyway. It's also not possible if the model is very complicated, like if it has many structural structural changes and changes in the parameters. But it's worth thinking about what you could do to interpret these models. Unfortunately, so the reason I'm treating simple linear regression in such detail is to illustrate issues like this that happen with linear regression, but often don't happen with other machine learning models, which is kind of unfortunate. And this is one reason why people still use simple models, because they are interpretable. Because if there's a question about, well, why are you predicting in a certain way, then you can answer it with simple models where you may not be able to answer it with more complicated models. Okay, so we're nearly at the half-time break. So let me quickly mention one or two other issues, and then we'll come back and we'll talk about multiple regression. So, so we talked about B, the slope of the line. The intercept is set so that the regression line goes through the mean, so x bar, y bar. So so why is this useful to know? Well, we saw it on that plot, that the mean is on that line. If you're not sure about that, you can check that with the equations. So we can think about, subtracting maybe the these values. So we could subtract the mean, and then we could also subtract the mean from all the y values and get a zero intercept. So it actually would go through the origin. Now, another point, and I guess this is the last point I'll make before we take that break. The sum of the residuals, remember all these differences from the mean squared, is going to be, that's this thing here, is going to be 0. And you can actually check this solution, and if you're not sure, if you're not convinced, check that reasoning. So that has a practical implication. So you can think of it as a constraint, right? So you're trying to find a line, and you're applying the MSE loss, and you're forcing the line to have these properties. So that means that depending on the data, some data points can affect the line more than others. And in particular, points that are far removed from the line, because you're looking at squared errors and because of these constraints, that can move the line around. These are known as outliers. And there's always a question about what to do in this case. So here's another reason why you might want to look at linear regression. For example, when you're starting a machine learning project, you might want to look at various dependencies of some of your data features and the output, because that can identify points that seem to have an adverse impact on the model. Now, you've got to be careful. Let me actually go to this example and I'll talk through what's going on. So the explanation is on the next slide. But taking the same data that we had before and changing one of the values, this green point here, let's just see. Yeah, so this is a y value for whatever this height is, that is increased by 10 kilos from what it actually should be according to the model that was used to generate the data. So what's happened here, so the red line, which is, so the blue line was the true model, the hidden target distribution. Noise was added to generate the blue points. And now let's suppose someone wrote down the value, the y value for the green point incorrectly. And then you fit the model. Instead of getting this red line, which we had before, you get the green line. And you can see that It's not dramatically different, but this is a very small sample of data. So that outlier has a considerable effect. Just one outlier has a considerable effect on the data. So there's always a question about what to do about this. But the minimum that you should do is look at the data and see whether or not you think that that's really an exceptional case that you might want to pay attention to, or whether it's an error and you want to remove it. And there are lots of machine learning techniques that are based on outlier detection. I probably won't say any more about that on this course, but this is a nice illustration of that issue. Okay, it's 5:02. Any quick questions? Okay, let's take a 10-minute break, and we'll be back for those on the recording in about 10 minutes. So see you then. Okay, let's resume. So I was a bit worried about this, but you're all absolutely right. I just made an error in that multiplying through. So yeah, that is correct. So yeah, it should be plus. So in this thing here, as you pointed out, I got the wrong thing in my notes. So just be careful with writing things down. And then yeah, we just took the b's. We took the b expression on this side over to the left-hand side with the other b, and yeah, derived that through. Okay. So apologies about that, but I think we're okay now. All right, so I want to talk about multivariate regression because very often you don't just have one input value. In fact, that would be the exception. So let's go through. So what I'm going to do is motivate and outline multivariate regression. I'll take a little detour into vector matrix notation, and then hopefully there'll be time and I'll try and do the derivation of multivariate regression in using that notation to sort of try and motivate it. If I don't have time, again, as I said, I'll post a link to a video in which Omar goes through all this in proper detail. And the reason we want to do this is we're not going to be, well, we are going to have some vector matrix representation through the course. But in the rest of machine learning, for example, if you do the neural networks course, basically everything is multivariate and it's all essentially vector matrix calculation. And also in probabilistic machine learning, which is more the realm of COMP9417, if you do that, then it's all that kind of thing. So I want to just get into that. We don't do a huge amount of it on this course, but we do want to do something. So I wanted to introduce it in week 1, so you kind of know what to expect. All right, so here's a very old data set. This is called the CPU data set. It was introduced quite a while ago, as you can see. Basically, we have a bunch of data. This left hand, this is the index of the data, so you don't actually include this. And then there's 1, 2, 3, 4, 5, sorry, 1, 2, 3, 4, 5, 6 features. Doesn't matter what they are. And what you're trying to do is predict performance based on these configurations of computers. So it's a very small data set. There are a few of these classic data sets around. The iris data set is a classic for classification. House prices is another classic data set for multivariate regression. CPU data set is what I'm showing you here. So what you want to get to is a model of performance in terms of the variables that you've been given, the input variables. So it doesn't matter what these are, but this is the kind of formulation you'd get. So we have 6 variables, and then we have like a 0th variable, which is the A, or the offset. And then we need to estimate coefficients for all of these, and then we add them up. So this is a linear model. The only difference before is that we now have 6 variables in terms of which the target is predicted, the class, the output is predicted. So in general, we're going to say the data has P, sometimes M, doesn't matter, P for parameters. It has P numeric features, and we want to predict a numeric value, so regression would be a good starting point. The output is a linear combination of attributes or features. Now, the form, as we saw there, is we have an initial coefficient. Now, there's a missing 1 here, right? So B0, so we're going to have P plus 1 coefficients or parameters, or weights, if you prefer. And there's a missing 1 here, which is going to be useful. So you can imagine it's B0 times 1, the constant value 1, plus B1 times whatever value X1 has, and so on. So the X1 here, so I'm just going to give you a warning. I'm going to jump around a bit with this notation. So sometimes the subscripts will denote an example index, as they did before. So when we said xi before, we meant the ith value in 1 to n data points. Here, I'm going to change it a bit, and I'm going to say the indexing here is on the dimensionality, so it's the number of features. So we have feature 1, x1. So if you imagine the CPU data, right, we've got, this is example 1, and this is, but in this indexing that I'm first introducing, this is x1, the first component of a 6 vector. There's 6 values, first component, second component. So we need a coefficient for each of these. So x1, b1 is the coefficient for x1, b2, and then all the way up to bp is the coefficient for xp. So there are p equals 6 in this case. They're actually p plus 1 parameters, so 7 parameters. So that's what this means here. Now I'm going to, just here in these few slides, what I'm going to do is denote the index, so example 1, example 2, example 3, or instance 1, 2, and 3. The first training index, I'm going to denote that index in this superscript bracket 1. Okay, so that's what that means. So the first training instance, the predicted value, the y hat, if you want to think of it as that, is going to be the b0 parameter value times x0 for the first example. And we're going to see that that's always going to be 1, the constant value 1. And then it's going to be b1, the second parameter value in the model, times x1, the first component of the first data item, right? So in the actual data, it would be the first component of the first example is the number 125, right? The first component of the second example is 29, right? So that's what it means. It's not difficult, it's just a bit cumbersome to get started, but we'll see hopefully when we move to the matrix representation that it's all pretty straightforward. So that's what that means. So we can represent that as just the sum I0 to P of the ith parameter value or weight or coefficient times the ith value of the first vector. So for example 1, instance 1, that's what that thing is, right? And the predicted y is going to be this sum here. So they're going to be, so I, in this case, I is varying over, is an index over parameters. So we have p plus 1, parameters, weights, coefficients. These are all synonymous in this context. And as I said, the first one is always 1. So it's just like a dummy variable because we need, you can think of this as the intercept. But because we're in now 6-dimensional space, or 7-dimensional space if you want to think about it like that, that has, we have to have a value for that to make that summation go through. Why do I mention this? Well, because we need to think about what MSE looks like. So MSE, difference between predictional and actual values. We've got p plus 1 coefficients, and we want to choose that our loss function is going to be MSE. So we need to choose the parameter values, these p plus 1 parameter values, to minimize MSE, or SSE if you want to think about it like that. It doesn't really matter. So I'm expressing it here in terms of MSE, and I'm talking about sum of squared errors. I'm just overloading this idea. So it's very straightforward, right? It's just that thing that we said. Now I'm indexing over J, just to try and keep the notation separate, for examples. So there are n examples, or data points. Sum over each, the difference squared between the y value for the jth example and that thing I had on the previous slide, which is the y hat, right, for j. Right? So you can see that I'm indexing over j in the example, and then I over the parameter space, squaring it. Straightforward? Yep. No problems? Okay, good. So this is conventionally known as ordinary least squares. In fact, the simple linear regression that we looked at before is also ordinary least squares, but we just had one variable here. So this is like the general case of that. Now, so we're going to derive a solution, if I have time, in terms of this loss function MSE for this model class. So we're essentially doing the same thing. Remember we said the steps at a high level, the steps we do in machine learning are pick a class of function to the model class to fit to the data, pick a loss function to tell you, how good the model is, essentially, and then have a method of fitting or optimizing. And it's going to turn out, in this case, that we can still derive equations. In general, for many of the subsequent lectures, that's not going to be the case. We're not going to be able to just derive a solution and say, there you go. Those are the values of the coefficients. But in this particular case, we can do it. So we will show that. And just on that, we're using squared error here, but we don't have to use squared error. And in some cases, we might prefer to use a different loss function. For example, we could just take the absolute error, and that might have some advantages. For instance, one advantage it might have is on that outlier problem I told you about just before the break. The fact that you're squaring the error kind of emphasizes, in a sense, the outliers, the effect of the outliers on the model. Absolute error doesn't have that squaring effect, so it may be better for you to use absolute error. And then there are other things that we can, other ways in which we can extend this loss function to do a different kind of version of the fit. So it all depends on what it is you're trying to get out of fitting the model to the data, what your application requires, and that will lead you potentially to choose a different loss function. You might ask, why is mean squared error then used? Well, there are a few answers. One is that it has some nice properties. I think the main reason is that it's essentially mathematically quite convenient and allows you to do the kind of derivations that we're doing here. But by no means is it the only approach. It's very widely used, though. Okay, so if we're going to solve this problem, what is the solution going to look like? Well, before we had a plot where all of the distances from the regression line were shown. And we said, well, what we want to do is minimize over those. So what that looks like in multiple dimensions is essentially the same thing, but now instead of a line you have, well, if we extend it to 2 dimensions, 2 data dimensions, or 2 feature dimensions, we've got x1, x2 here, we now have a 3-dimensional, we can do a 3-dimensional plot. For the CPU data, we'd then we'd have 6 dimensions of x, x1 through to x6, whatever those variable names were, and y would be a function of those. So we can't draw a solution to that problem in in 2 dimensions. So we're going to not do that. But you can do it for 3D. So it's going to be a plane in 3D. The solution, I mean the function that we want to find, the model, parameterized by the coefficients. Now, you might say, well, technically we've got 3 dimensions because we've got x1, x2, but we also have x0. But remember, x0 is always a constant value 1, right? So we do have a parameter for that. So that is, you can think of that as the value here. And the solution is going to be a plane. And in general, in more dimensions, it's going to be a hyperplane. But that's too hard to visualize, so we'll just think of it as a plane. But the idea is identical. So here are the points, the red points, and it's the vertical distance that we're trying to minimize. What else do I need to say? Okay, so that's the problem in a nutshell. Now, notice down here, I haven't been entirely consistent through this slide with this notation, but what I do want to highlight here is that we have y hat as a function of x, and x here I'm denoting in bold to kind of indicate that this is now a vector. It's actually going to be a matrix, but nonetheless, okay. So instead of a single x, it's now a list of x's or a vector. Okay, how are we doing? All right, so I thought it might be useful at this point. For many of you, I'm sure you already know all of this, so I'm going to go quite quickly through this. And this is just like a grab bag of things I thought that it might be useful to highlight at this point before we get into the matrix vector representation that we'll use. So in order to leave enough time for trying to do the derivation, let me go quite quickly. If you're not sure about this stuff, then go to the Mathematics of Machine Learning text that I've linked in the course outline. And all of these are just things I grabbed from the first chapter, which is a really nice, very comprehensive overview of this kind of stuff. It actually has a lot more detail than we need in this course, but if you're going to go and do a lot more machine learning, it's a good idea to read that chapter and at least have a sense of what you might need for various different kinds of machine learning. Okay, so we call a normal number, a real number, is a scalar. You can also think of that as you can even think of that as a matrix. It's a 1-by-1 matrix, but let's not get into that yet. So a vector is just a collection of numbers, and we typically, so conventionally, at least I'm trying to follow the convention in that textbook. There are actually slightly different conventions for writing this stuff, so that's where I'm trying to be consistent with. So it's a column vector. You can, if you're programming in Python or some other language, R or whatever, you often write vectors in line, just as a list, or you can think of it as an array. You can think of this vector, this column vector, as an inline version. And this is where you've got to be careful. Different authors use different notation. So this is parentheses. This is using brackets and no commas. And then this T here is just called, it's an operator called transpose, which just means change, essentially it means change a row into a column. So a vector is an element. So in this course we don't do anything with we'll just assume that all vectors are real valued vectors. So we say this math notation just means real numbers, and it's an n, so it's r to the n, right? Or rn is just what people say. So a, so this is supposed to be a bold a, little a, and this is the column vector, and it's got 3 components. So the vector comes from the space of all 3 vectors whose components are real numbers. So if you're not familiar with this stuff, just think about it as an array in a programming language, right? So the order is important. That's the key thing. Vector addition is component-wise. So you can add 2 vectors of the same dimensionality. So A and B have the same dimensionality. They're both in Rn. That's what this is, just the set element symbol. I know that for many of you this is revision, but I'm just going to go through it. So you can also have scalar multiplication. There is a kind of issue with vector multiplication, but I'll get into that when we do the derivation. So let's just think of vector addition, scalar multiplication. So lambda is a scalar, and so the name scalar comes from the fact that you can think of that multiplication as sort of scaling it, right? Changing the size of the components. So that's all you do, right? So you take the scalar and you do the multiplication of each of the components, and then you get a new vector, which is also in the same space, Rn. Now, to sort of anticipate the derivation for multiple regression, I need to go more quickly. We can think of systems of linear equations. Now, this is an example which is in that textbook. If you're not clear about this is, go and have a look at that textbook. But this is just to kind of make clear that you can set up a system of equations and solve, and this is a common route in optimization. And in fact, the linear regression thing that we do is essentially the same idea, but instead of finding an exact solution, we find an approximate solution, because there can be an issue with this. But let's just go through this. So we have a system of products and resources. So think about it as like a laboratory, well, a factory or something like that, right? So the resources are what you can use to make the products, and you have a set of products, n products, and we have m resources. So A sub ij units of resource are I, using I to index into here. I needed to produce a unit of product nj. So we've got 2 indices, I, 1 to m, and j, 1 to n. So the convention here is that we'll index into the rows by I and the columns by j. So there are m rows and n columns, and hopefully it's consistent here. Okay, so these are these individual components are in R, and the coefficients as well are, the products, what are we calling them? Yeah, we're calling them products. Sorry, no, we're not. We're calling them resources. Gotta get mixed up. If that helps you, great. If you're not sure about it, go and read the textbook. It's all clear. But the point I want to make is that out of this bunch of numbers, we can collect these values and make the notation a bit nicer. So we can say all of the coefficients form a vector, because if you look at this, x1 is an unknown. So now here x is an unknown. You've got to be careful. The solution is x, right? So the general framework is that for us, x is going to be a data point, but in applications of this kind of linear algebra, x is often the thing you want to solve for, so they're unknown. Anyway, x, the thing to find, and a1 to m, a1 to m for column 2, and so forth can be gathered into vectors, and then this is also a vector. So we have m vectors, column vectors, and then we can collect these also together into matrices. And here I'm saying a vector is essentially a single column matrix. Okay, so this starts to get nice because we can then take that whole system of equations and say, well, there are basically three things that you need. There's this matrix of m by n, and then there's an n vector here, which is multiplying it, and the result is an m vector. Now, if you're not sure about this, you need to go to the textbook and check that you understand matrix vector multiplication. So I'm not going to go through that. I'm sure nearly all of you know that already, but just to confirm, if you don't, go and check it out. And the nice thing about this is we can dramatically simplify the notation, right? So that whole thing is now written as A, the matrix, times X, the X vector, the unknown, and B, the solution, if you like. I'm not going to go through that. Okay, just on the notation, the mn vector is, each component is an R, and the whole matrix is an element of this space, m times n. Now, in programming and machine learning, you often need to take a matrix in some form and change its shape, change its dimensionality. And a very simple version of that is you just turn a matrix into a long vector. And the dimensionality of that long vector is now going to be m times n. So some people say m cross n, just to differentiate it from this, rmn, or m by n, same thing. But this is an operation you might often need to do, change a matrix into a vector. I'm not going to talk about matrix summation. Matrix multiplication, I just mentioned quickly. The key thing to remember is that the interior dimensionality must match for this to be well defined. If that's not the case, so if you're multiplying A and B, this is okay here because A is an m by k, or m cross k, and B is a k cross n, or k by n. And so the matrix multiplication, essentially the rows of B match the columns of A. They must be the same dimensions, otherwise that's not gonna work. And then the resulting the result is the dot product of each of those vectors, which is written here in component form. I'm actually going to skip over this. I'll just leave that for the time being. Some matrices can be inverted. If they can be inverted, then we write them like this. Not all matrices can be inverted, but that's what this means. A to the minus 1 is A inverse. Right, let me... Okay, there's a bunch of other stuff, but I'm not going to go into that. All right, let me quickly see if I can, sorry, that shouldn't be there. Anyway, linear regression with multiple inputs, multiple regression. So we're going to say that this model that I talked about before in terms of the individual data points, we have a loss function. I've written it little l, just like before. This is the thing that we had. But the model can be written in vector matrix notation. So y hat, predicted y values, equals x, the matrix x of all of the rows and columns in the data for all of the x's, times theta or b or beta or whatever, weights if you want, it doesn't really matter. So here's what that is. X is an n by p plus 1 matrix. Theta is the vector of the parameters, p plus 1. Y is the labels, the actual values in the data, and then y hat is the vector of predicted values. Okay, so here's the solution. So let me try very quickly go through the steps for that. We'll see how we get on. Okay, so what we're trying to do is the same process, but now with these with this setup for vectors, matrices and vectors. Those are the things that we need to find. All right, that's on. Right, so hopefully my notes are correct for this. Let's see how we go. Right, so we've got, let me write it like this to just get started. We have MSE. So we want to find, I'll use the notation B, so we've got B0 up to BP hat. Okay, and we want to find that by minimizing the MSE, so argmin. So if you're not familiar, I should have mentioned this, argmin or argmax means we're trying to find the values that minimize or maximize the function. So we want to find the values for, in this case, B0 to BP that minimize MSE. So what's MSE going to be? 1 over n sum, I'll just write it like this, I to n. So we have so I'm actually going to skip the oh no, okay, let me put it in. So it's the ith example y hat minus b0 times 1. You'll see where that comes in. bi for the ith component, sorry, B1, that should be. You've got to be careful with this indexing. So it's the ith example, the ith data point, the first component, that's x1i, and then minus all the rest, so B2, B3, up to BP on the component P, the final component for example I. So we take all those away from, take that linear combination away from the y hat, and hang on a sec, I think that's wrong. This should not be y hat. So that is a mistake in my notes. Should be y, right? And this equals to I hat. And then it's squared error, so you need to take the square. So if we did the same approach as before, we would take the loss function. So the loss function is now B0 up to BP, right? So if we took the same approach to minimize, we would need to take each component separately, like we did for A and B. So d of the loss function B0, that would correspond to A that we had before. This would correspond to B1, and so on, right? So we'd have to do the same process for all of them. And, that could be, and then we'd set that to 0, right? Set that expression. So that would mean we have, so we got p plus 1 parameters, and we'd have to find so before we had 2 parameters, we had A and B. So now we'd have to find p plus 1, and each one would have to be a derivation to get to the normal equations for those. But we can use the vector vector notation and use calculus and linear algebra on those to get the solution. So the solution would be the B vector. Well, what we need is this. So this would be the solution. Now this is going to be a vector B0, B1 up to BP. So this is it's a vector, but we'll say it's also a matrix because it's a one column matrix. So we'll say it's in R P plus 1. So technically, it's the matrix. It's the vector in R P plus 1, or it's a matrix in R P plus 1 cross 1, right? So it's one column. P plus 1 rows, 1 column. Y is, so that's in parameter space. B is in that parameter space. Y is in data space. So it's now going to be Y1, Y2, all the way up to Yn. So this is going to be a vector in R what? N. Okay, now we've got n of these y's. Those are the labels, the outputs. Sorry, don't want to get too far away from the mic for the recording. So let's say we have the ith data point xi. So this is also going to be a vector, but we think about this. So we have p plus 1 parameters, and so therefore we need p plus 1 components of the data point. So we've actually only got p components of the data point, but we have one extra for the offset parameter. So we set that to the constant 1, the value 1, and then we have xi1, xi2, up to xip. And that is also, well, what's that in? P, yeah, p plus 1. And then we can take that as the matrix X, which is essentially your whole data set. And this is where you start to see some compaction. Oops. So this is going to be a matrix. Now, all we have to do is take each of these. This is the ith data point, so we need to take each of the data points. But what we want to do is transpose them, so that we have our familiar rows for each data item and columns for the features. I mean, we don't actually have to do that, but that's the way that we typically present the data. So we'll say that this is x1 transpose, x2 transpose, and all the way down to xn transpose where each of these is one of these guys. Okay, so this must be in R what? What's the dimensionality here? Yeah, and I'm really not going to have time to finish this derivation, but let me try and start it and show you the result, and I'll just have to refer you to the video. So just to be clear, I'll just write out the data again. So just to be clear, what we need to have is a column of ones. Okay, that's for the first parameter. Then example 1, column 1. This is like column 0. Example 2, column 1. Example 1, column 2. Example 2, column 2, and so forth, up to example 1, column P, example 2, column P. These are all ones, so example n, column 1, example n, column 2, dot, 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 example n, column P, and so forth, right? So that's the data without the labels. Okay, what can I tell you that will sort of make sense? Okay, so, well, because we've now got a column, now we've got a vector of the parameters that we want to find, we can say that the loss function is a function of those. That's vector B. So what is that? Well, that's mean squared error, so this can be written like this. And now I'm back to, okay, I just need to be, I just need to emphasize what I'm doing here. So now I'm back to indexing I is over the data set. And then I have B transpose xi squared. Now, why is this okay? Well, if I have my B vector here, and I have an xi here, an example, what I'm doing is, if I didn't mention, I don't think I mentioned this. Okay, so if I take these two vectors, this thing here is called the dot product, or the inner product. Okay, so the inner product is this thing here. It's B, and if I take the transpose, B transpose, and I take xi, B transpose xi, what does that actually equal? Well, it equals the sum of B0 1. Hang on, sorry, let me. B0 times 1 plus B1 times xi1 plus, and so forth, right? All of the elements here times all of the elements here. That works because they both have the same dimensionality, right? They're both in R, they both have P plus 1 components. The first component of the x vector is 1, so that's okay. And then I have all of the other values for the x vector. So that gives us BP x I P. Okay, so that is like the sum of all of these the sum of products over that thing. So that is what this thing here is doing, right? So if you think about it, that is the same as we had before with our A and B parameters. Now we're collecting all of the parameters into B, and we're taking the dot product of these things here, like that. And it's squared. Okay, so I've only got 5 minutes left on the recording, so let me just maybe do a couple of quick steps to give you a sense of what's going on, and then we'll quit for this week. So if I oh, actually, there's one more simplifying step that we can take. Now, if we look at this summation, we're going from 1 to n, right? So we're going from 1 to n. For each of the I examples, we're saying, well, what's the label? What's the prediction? B transpose xi, square the difference, and then sum them all together. But we already collected all of the data in this matrix, right? So we've actually got all of these xi's. We've got xi, x1 to xn, which are just collections of these things here. So this dot product and this dot product, the dot product of this and this can be found by multiplying each row by b. And we write that by, well, we can write that in a couple of ways. I'll just write it like this. So it's y, the vector. Oh, that's one other thing, right? So we've also got the vector, this vector here, right? So we've got y, the vector. So what we need to do is say, well, for each component of this, there are n components of this. Take the dot product of the corresponding row, so y1 with x1 transpose b, or b transpose x1. Doesn't matter. You can write this in either way around. Okay, so the shorthand way of saying that is this: y minus x, all of the rows, times the parameters. Okay, so what you're actually doing in here is taking this b and multiplying each of the rows, and then you get back and subtract the vector. So you're doing all of the operations inside this one thing. So you're doing all of these operations inside this one thing. Now, there's a square. Now, in this notation, we don't actually typically write this as a square operation. So let me just take a bit more space. So the way we write that is it's 1 over n, all of the y labels minus the product of the parameter values times the data, x. So that you can think of this as the y hats. But we need to square it. So instead of squaring it, we do the same thing as we did before. We take the transpose and we multiply it by the same thing. So you can think of this as squaring it. Now, I'm not going to have time to go through it, but what you then do is take the derivatives, set them to 0, and solve. And at the end, you're going to get the result that we had on the slide. So I'll just, there's a bunch of stuff that happens here. And what the solution you're going to get is b hat, we'll call it hat because it's an estimate, is the big matrix times itself, x transpose x, inverse, and then x transpose y. And that is the solution. This is the least squares estimator, the solution. And you derive that by essentially doing the minimization and the calculus steps that we did before. And this is called the least squares estimator. So least, oops.